Rick, thank you so much for coming. Everyone, this is Rick Manor, Executive Director of the Champaign-Urbana Sanitary District. And you have quite an operation here, right?
Yep.
So how many people does this place handle the waste for?
We handle Urbana, Champaign, Savoy, and the unincorporated areas, overall about 140,000 people.
140,000 people, wow. And every time a shower drain goes down, or a toilet's flushed, or the sink goes, or the dishwasher runs, it all comes here.
Right. Every drain inside a house, or a business, or an industry, all drains into what we term sanitary sewers, which come to this treatment plant, so that we can clean up the water before it goes into the nearby creeks.
Excellent.
Which is what we do with the water when we're done, is it's discharged to the waterways.
Right, right, excellent. So how much water is that? What's your total amount you treat in a year?
At both of our plants, in total, we do about 20 million gallons a day, which is about 13,000 gallons a minute. If you want to picture that, if you picture a room about this size, or your bedroom, picture filling that up in about a minute. That's what we do every day,
minute,
365 days a year.
20,000, so we got 400, so that's what,
every person uses directly and indirectly about 100 to 150 gallons a day.
Wow.
People don't believe that when they first hear it, but when you flush a toilet, it's 5 gallons. You take a shower, that's 20 gallons. You wash some dishes. And then in addition to that, all the related business flows.
Right.
That you go to a restaurant, or you get some clothes manufactured, that uses up water. And power production uses water. And then there's a wastewater stream associated with it.
So everything in your everything in your environment, everything that you use, it's between 100 and 140 gallons per day per person.
That's a general
rule. We have 140,000 people you're taking care of. Do the math.
There you go. You get to 20 million gallons in a day.
Here, 20 million a day, and 200 days, it'd be 4 billion. So we're close to 5 billion gallons a year.
Actually, we're 365 days a year, because you still want to do your life on Saturday and Sunday.
So
we're up to 7 billion.
7 billion gallons a year through here. I met this guy because he came and gave this awesome talk to my Rotary group. And then I read all your slides again last night. So there are 2 things in the quiz that you need to remember. All right? 200 parts per million.
That's where we start.
That's where you start. Now that is really small, right? 200 parts per million, that would be 0.2 parts per thousand. That's 0.02%. That's the amount of solids in your waste. You don't think that. You really think, most people, you ask someone, I don't think it's maybe 1%, right? Or higher.
Right.
But that's only 200 parts per million of solids. Almost everything coming here is water.
Right.
Of course, that 200 parts per million is not something you want to consume.
So that typical wastewater starts off at that much pollutant, which is very little pollutant, but it is of a nature of solids that it's unacceptable.
Right.
And so that mixture of waste is unacceptable to go into the environment. The reason our treatment plant is here is to change it from that unacceptable sewage characteristic to acceptable to go into a water environment a relatively safe manner.
And the second thing, because I did learn from his quiz, the second thing is when it leaves, it's at 4 parts per million.
We're down into single digits, right?
Single digits.
So, we're working on the very edge of that curve, and we need to get out those last bits of solids to make it acceptable to go into a creek.
Excellent, excellent. Now, as I also learned, there are 5 steps in this process, and now we're going to go outside and see those 5 steps. And correct me if I get this wrong, but I think the first thing is filtration. Get out any large pieces that happen to fall through.
We term that screening because there's later filtration. So screening because we're talking about taking out large chunks.
Okay.
Things like sticks and debris and plastic items and various stuff.
The things my grandchildren flush down the toilet.
Right.
Got it. Okay.
So beneath your feet are 4-foot diameter, meter and a third sewers coming into the plant. All of the flow from inside anybody's building is coming in here. It's all mixed up together. And what goes on in our first step here is called screening. And so you can see here we've got 1/4 inch, 6 millimeter holes. The sewage comes through here, And if you can see in that gap, you see this screen is in the main flow, and anything larger than this gets caught up on the screen, rinsed off, dumped into a dumpster to go into a landfill.
Wow. I don't suppose you try to claim like the diamond rings and everything else that comes through.
About every couple years, somebody comes along asking them to find their diamond ring, and we tell them, sorry, you're sort of out of luck. Because what we have is a big pile of debris when we're done.
Yes.
And so, yes, your individual ring, if you flushed it and it's gotten out of your house, it's gone.
SOL.
Pretty much.
All right. And by the way, since this is where all the raw sewage is coming in, it does smell a little bit in here.
Right. Recognize that we're here to take out that pollutant, so that's at the beginning of the operation. Yes. At the end of the operations, it doesn't smell at all because we've cleaned up the water. So the reason, right now the water is unacceptable.
Right.
The odor is probably unacceptable too, at least if you're not used to it, but it gets better as we go through it.
All right, let's look forward to that. And now the second step is you let certain microbes eat all the things they can.
Correct.
Right, it's open smorgasbord for the microbes.
Right.
And you have big open kind of ponds where they go through and they convert all those solids probably into water, carbon dioxide, things like that.
Right.
Right.
Our job is to keep those billions of microbes fat, happy, and reproducing.
Fat, happy, and reproducing.
That's exactly what we want to do. Is we keep them growing as optimally as possible. Because as a natural part of what they do, they take waste and use it and convert it into cellular matter and to convert it into less obnoxious forms when they're done.
Right.
And so by doing that, we convert a lot of the waste into cell mass.
All right, okay. So here we are. This is step number 2.
Right.
This is the beginning of the buffet.
Right.
For the microbes.
Right.
Ah.
And so what we have here is the mixed liquor, the combination of the microbes and all the food and everything else that is from you guys, from your waste. And in here we provide a lot more oxygen. And the reason for the oxygen is to make sure the bugs stay aerobic and that they have the food, the oxygen to respire and to continue their reproductive cycles.
So you're just pumping air in, right?
So yeah, I mentioned our $750,000 electric bill.
This is a big
the
part
vast
of it, huh?
majority, a good fraction of it is for our electric, is for the blowers.
Okay.
That our blowers cost us a couple $100,000 a year to run. And that's just to provide air so that the microbes can do their reproduction.
And you don't have to worry about keeping this warm? Is it warm enough? Or
it's warm enough that in colder climates you do worry about it actually freezing, that further north you'll cover these tanks.
Okay.
But recognize that the sewers are down 6 and 10 feet into the ground, and so they're at the average temperature for your climate. Here 50, in East Central Illinois, we're in the 50s to 60 degree range is what the earth is at.
How long does the water stay in the ponds for the bugs to eat everything?
That's a critical point about our overall operation, that we do what nature does in the course of 12 days. We do it in about 12 hours.
Okay.
That our operations here are very much mimicking what nature does in terms of how it deals with a waste load into a water environment. Things settle out, microbes feed on the waste and reproduce on it. And then eventually, as the water gets 10, 12 days downstream, eventually your waste is removed.
Okay.
But since that's unacceptable with our population at 7 billion across the earth, we now need to remove it ourselves because of our density of population.
Right, so 12 hours from input to outflow.
Correct.
Wow, excellent. And this doesn't smell near as bad, right?
Right.
So we're outside. Okay.
We're at about 3/4 of the odor has been removed. There's a little bit of mustiness because of the high humidity.
Sure.
And you can tell that something's going on here, but it's not nearly as noxious as what it was
And those
earlier.
bubbles, is that from people's phosphates and soaps that are in their water stream? Or?
Anything that makes the water more stable is a surface active agent, a surfactant. There's a lot of those that are not soaps.
Okay.
So just if you mix enough food and such, you find that there's a fraction of it that encourage the lasting of the bubbles. And then in addition, remember, we're bubbling billions of bubbles down below us, and some of them accumulate to make the larger bubbles at the surface.
Okay. So step 3, settle, because the bugs sink.
Right. So yeah, the bugs do a nice job of taking that waste and essentially...
They're fat and happy, they can't eat anymore,
right,
and they settle out to the bottom.
Correct.
All right.
And by doing that, we now are separating them from the water and cleaning up the water.
Right.
So they do all their work, and then we settle them out and separate them from the water. We need to bring back some of those bugs back to the front end of the buffet table, if you will.
Got it.
And so they keep on going around in that circle for about
and
a week or
reproducing,
two.
and some of them dying,
Right.
and then they probably get eaten by their fellow bugs. Right. Okay.
Right.
And they never get out of the waste pens.
So
Got it.
they do the majority of that work
Okay.
by that
Okay.
cycling.
Okay. So then that third step is you settle it.
So this is one of our settling tanks. This is actually a primary settling tank. Normally we're talking about secondary settling tanks, but you guys probably won't care about the difference too much.
No.
The process is very simple and similar. All of our tanks are about 10 to 15 feet deep. In this case, the flow enters the tank at the center,
Enters in the center. Okay.
comes underneath that collar, and then travels radially outwards to the outer edge, and then comes up under this collar, and then overflows into the weir trough and out of the tank. So the key is that we get our time from the flowing from the center of the tank out to the outer rim. It takes about an hour for the water to travel from there to here. And in that hour, you get the gravity separation of the solids settling out to the bottom of the tank. The solids are removed from the bottom of the tank in a separate stream, and then you can see the water overflowing here on its way.
So you still pump the sludge out of the bottom, which are the bacteria,
Right,
and then you return them back to there, most of them, or
Right.
some of them,
most of them.
because they're multiplying, obviously.
Right, so you have to take out the amount that's produced in any given day,
Right.
but that's all you have to take out. So about 90% of the bugs go back to the front end of the line today, and then about 10% are removed because of the
And
growth.
that becomes landfill too?
Actually, we end up turning it into a fertilizer, a soil amendment, to get some useful
Sure.
byproduct of
Sure.
it. And at that point, we have to treat it further to make it amenable for going out into farmers' fields. That's called anaerobic digestion. But once we're done, we're producing a fertilizer soil amendment,
Okay.
which
And you
is
can
called
sell-
biosolids.
And you can sell that, right?
We don't actually sell it. The farmer gets it for the inconvenience of us going onto their fields, so they get it for free.
Okay.
But they get a free fertilizer for a couple of years.
It's like
here
I
for
used to
free.
have a horse business, and we had a manure spreader, and
That's
we
it.
tried to convince the farmers to let us spread manure in their field.
And that's it exactly. And
Right.
so we have that same arrangement.
Okay.
We use this over about 200 acres in a year.
Okay. Okay.
All right.
All right. So we've settled out and returned the bugs to their dining room
Very
after
good.
their nap.
Yep.
Okay. Onward. Let's follow the water.
All right.
And now you filter it.
We
again?
actually have a second set of bugs in our nitrifying tower.
Oh, nitrifying. Okay.
Right.
Okay. So now step number 4, you drop this stuff basically through the air.
Well, the towers are about 70 foot tall, and they've got a lot of plastic media in there.
Okay.
And so by splashing the water on the media, the microbes grow on the surface, and so they get exposed to water, which
Right.
includes some of the waste,
Okay.
which is their food essentially.
Right.
But then also, when it's not splashed with water, there is oxygen from the air
Right.
that can come into the water,
Right.
so that they can respire.
And you call it nitriting? Is it just because of the 80%
Nitrifying.
nitrogen in the air, or?
No, because what we're taking ammonia and proteins and amine groups and turning them into nitrate.
Got it.
And so that's nitrifying bacteria are the ones that do that
So the
conversion.
bacteria will take the ammonia, those types of things, out of the water and turn it into nitrates, which will be a solid.
No, it's actually still dissolved.
Still dissolved.
Still dissolved. But the main difference is that ammonia is very much of a fish toxin.
Okay.
And so in order to help protect the fish, we're converting from a relatively toxic version of nitrogen to a less toxic one, nitrate.
Okay.
And so that's nitrifying bacteria, and that's why we call them nitrifying towers.
Nitrifying towers. And so that was step 4.
4. So what's going on here is the water is coming out of the carousel and spraying onto the plastic media, and then it goes down through the cracks and crevices between the media, and it works its way down. And as it's working its way down, it's going past thousands and thousands of microbes that are using the water and the food in the water for their life and reproduction.
Wow.
And so that's all this is a big area for microbes to set up home on.
There's a lot of surface area.
That's the idea.
A lot of surface area. Water just trickles through.
And then the air comes free. In this case, we
Right.
don't have to use a blower we use the natural convection of the air.
Right.
So
this
it
is
costs,
a lot like a cooling tower for a power plant, in a way.
in some ways, yes. So it costs us here in terms of energy to bring the water up to the top.
Right.
And that's you pay for it one way or the other. Either you pay for blowers down there,
Right.
or you pay for
For
pumping
the
the
water
water
pumping
up here.
And how long does this take for this water to just fall through this tower, the plastic channels?
It's probably less than a minute.
Less than a minute. That's enough for the microbes to grab the stuff
Actually,
and
no,
turn
it's probably a little more than a minute. It's a couple minutes.
a few minutes, and that's enough for the mostly the nitrogen in there to be attached to the bugs that are eating it,
Right.
and turning it and basically adding oxygen, nitrating it.
Right, and the bugs have a biological imperative to find this food,
Right.
and so they do it as fast as they can.
Sure, they're hungry.
Right,
Do you have to worry about growing too many of them, or some of them just fall off when they get too big?
that sloughing off is actually the natural byproduct of that. As the
Okay.
layer gets too thick,
Uh-huh.
the water coming by knocks
Takes it
off
off,
the extra
so you don't even have
surface.
to clean the place.
Right,
Nice.
it's sort of self-cleaning.
All right. Step 5, a filter before
There
it
we're
goes.
at filtration. right.
Filtration.
And the key is that earlier filtration was very gross, large particles that 6 millimeters, quarter-inch type
Okay.
material is what we're taking out at the front end, where we call it screening. When we're talking about our final filtration, we're talking about down to the micron stage, and in the 10 micron range.
Wow.
We're now going across a fabric filter, which essentially looks just like a plush carpet.
Okay.
And the carpet lays down, the carpet fibers lay down on themselves multiple layers deep, and then with that we actually take out particles down to the micron size.
Right.
very
Now,
efficiently.
don't those filters get clogged up?
Well, that's the thing, is that what we do as engineers is we design things to work reliably and do it in quantity and do it repeatedly. And so the filter is actually probably the 10th generation of technology that we're now at, a very high-tech fabric filter that does a good job of laying itself down, taking out the particles for hours at a time, and then once it starts to get clogged, all we have to do is back flush it with a little bit of water. The filter releases itself, the layers undo themselves
that is
with
so
that,
cool.
and that in that backwash cycle, then it takes that solids and takes it off, and then all it takes is stop backwashing the flow, and then the ply lays down again and becomes a filter.
A good filter again.
Right, and so
Wow.
that's a neat process that we've gone through a lot of engineering to get us to that high-tech version, but it's as simple as filtration, but it's as complex as what I just described.
Very cool. Well, let's go see it.
Okay. And we're at 90% of the way through the treatment plan. One thing that I like showing off is that we do have full computer access. That this is called the SCADA system, supervisory control and data acquisition. And so from these spots, you can actually see what's going on throughout the plant. And so here's our entire plant, and you can see what's going on in any individual building by just touching it. Here's the flow diagram of what's going on, telling us which pumps are on and which pumps are off.
So you press the wrong button, so you can screw everything up.
You could.
Yeah,
And
all
that's
right.
why we also have lockouts and password protection.
Good.
And that's why I'm not allowed to touch anything.
Even though
because-
you're the boss, right?
Right. I'm not an operator. I'm not the person who knows what's going on at any given time.
Hey, believe me, it's the same thing in my lab, right?
That's it exactly.
Yeah. Okay.
So, so what we have here is a screen, and we lay a carpet on top of this, and I'll show you the fabric filter. Like I said, it looks an awful lot like a carpet, and then the water flows through the fabric, through this screen, and then into this central channel, and then out.
Okay.
And then we were talking about backwashing or
Right.
cleaning the filter. Take that same thing, pump the water from the so that's where it's normally producing flow. That's how it's normally product. When you need to backwash, you take a pump it backwards for a period of time, pumps in here, goes outwards, and that's what releases the
And now
solids.
that's those solids that you release. You must capture them somewhere else,
Right.
because otherwise it would just go right back and clog it up.
Right. During
Okay.
a backwash cycle, that waste stream is then taken off and put back to the front end of our treatment plant.
Oh,
We're very
all
good
the
at
way
processing and
back.
cleaning up water.
Sure, why
Goes
not?
back to the front end,
Okay.
and then it gets settled out later on.
Okay. And how often? I mean, what percent of the time are you backflowing?
The backflow is usually a small percentage of the time,
Like
a couple percent out of
percent.
the, yeah.
Okay.
So a
So
couple
2%
minutes,
of the water recycles, basically.
right?
Okay.
And that's just to clean it up
To
and
clean
to
the
get going
filters.
again.
And how long before you have to throw a filter away?
The fabric filter itself can last a few years.
A few years.
Yes.
Excellent. Okay.
And then actually, Yeah, we'll just leave it at a few
Okay.
years.
And then, so this is the room, this is where all the
Right,
filters
so
are
it's a bit
underground?
noisier and splashier in there, so that's why I do the explaining out here.
Okay.
And then we'll go into there.
So the water's come through the nitrating tower, right?
Coming
and now
down
it's
to
coming
here.
in here, and you're gonna get the last little bits of solids out down to the, you said 10 micron?
10 micron
10
range,
micron
and
range.
now we're down into the single digits, 1 to 4 parts per million of solids when we're done.
Wow, so it's almost pure water, after this anyway.
It is still, it's very clean water, but recognize it's not at all drinking water. Drinking
Okay.
water has higher standards than that by far.
Right, and probably some chlorine and other things in
Right,
it.
and the nature of the waste, that 1 part per million is still originally from a waste product, and so
Right,
it's pretty
still bacterial
unacceptable.
or
It
other
is
things
not at
like
all
that.
meant for drinking
Absolutely.
whatsoever.
Absolutely.
And it's good enough to go into a creek, not good
Right.
enough to go into a
Probably
glass.
good enough to water a farmer's field?
Yes, that it would still be fine for irrigation. It's fine for that type of thing and for those
Okay.
types of environmental type uses, but not for drinking
Not
water.
for drinking. Okay. All right.
So the lighting isn't terribly good. You may even want to turn on your light. So here's the water coming in, and there you can see the edge of the filter.
Oh yeah, the edge. They're coming
It's sort of
edge
set up
on.
as a Trivial Pursuit pie pieces.
Okay.
6 or 8 of them in a thing. And so here's the edge of the water, the edge of the filter. So the water travels right to left through the fabric filter into the main channel, and then this is the product coming out.
All right. Here, come on in, guys.
And you can see the water starts off pretty darn clean.
Smells
and then
much
the final
better
product
than
is
starting.
even cleaner. And here's the fabric filter, so you can see what I was talking about. And maybe we'll go out there to get the ambient noise away.
Wow, it really does
All right.
look like a plush carpet.
So
Okay.
here's our fabric filter, and so like I said, it's sort of like a plush carpet here. The fibers lay down on top of each other to create the filter. And so when the water is being filtered, it's flowing this way, through here, into the screen, and then into the main channel and out. And then on backwash, the flow is, the backwards flow of that is in
Right.
from the channel
And all
up
the
to here.
fibers stand up, so
then
all
they-
the stuff comes off of it.
Right.
Very clever.
It is very clever, very smart,
Uh-huh.
very reliable, which is what we look at.
Yeah,
for-
because if this plant goes down, everyone's toilet backs up.
Right. So I mean, we have to be able to do our work every day throughout the year. When it's 20 below outside, we still got to work. When
Right.
it's raining cats and dogs, when it's 110 out, we still got to get to work.
And the extra water you pick up from the rain going into the open tanks is relatively minor.
What falls into the plant itself is relatively minor. The problem, we do end up having a lot of challenges because of sewers leaking, and
Right.
in particular, if people have connections from outside sources going into those sewers,
That's right.
we actually see
'Cause
flow rates that are much higher during
Oh, I
storm
bet.
events. and
Because
it's
the
much more
storm
challenging.
sewers are not supposed to come here, right?
Right.
The storm sewer, like the water that comes off your roof, that's just supposed to go into a river, right? It's just
Right.
rainwater.
Right.
But somehow their systems merge, or at least they merge into the sanitary sewer somehow.
There's some fraction of the storm water gets into the sanitary sewer, but because of how much more water is associated with a storm, I mean, a 1-inch rainstorm produces billions of gallons of water.
Right.
So just a small fraction of that leaking into the sanitary sewer causes us a great deal of challenge during storm events.
I bet.
And so a large part of what we do is trying to fight that to keep this storm water out of the sanitary sewers.
Because you really have no way to buffer. I mean, you have how many? 12,000 gallons a second?
A minute coming in.
12,000 gallons a minute. You
Right.
can't say, oh, hey, I'll just store it for a little while. No.
Actually, if you do, you can, but you need millions of gallons of storage.
Right.
And so that's what the Deep Tunnel Project is in Chicago, for example. And we're actually considering putting in a lagoon for storing some of that flow as well, but it's somewhat expensive. It's very large. You're talking
Well,
about
and
millions
then you
of
have a
gallons of
giant
storage,
lagoon of raw sewage.
which you then treat over the next couple days after the
Sure.
storm is done. So it's
Sure.
not like it's accumulated for a long period of
That's
time.
right.
It's called an equalization basin because it equalizes out your flow. Because the alternative is to just push it in through the plant.
Yeah,
and
and
what comes
they-
in has to go out, and it has to go out that much faster.
Which means that it's not as clean.
It's more challenging to get to the same level.
Right.
We still try and treat it through the same steps, but we can't quite get to the exact same numbers. And so
course.
there's some some understanding of that on the regulatory end, that during storms it's much more challenging.
Well, absolutely. I mean, and the alternative is nothing we want. So we are so happy you do your job.
And one last step, we'll take you to take you out to the creek to see the end.
Okay.
All right.
That is impressive. 12,000 gallons a minute of sewage in, 12,000 gallons of 4 part per million. Pretty darn clean water coming out.
Yep. And we get it done in 12 hours, and that's it.
And 12 hours later. And what's the name of the stream?
This is the saline branch of the Salt Fork.
Saline branch of the Salt Fork River. Well done, Rick.
Thank you
very much.
You're welcome.
This is what you need to know about sanitary waste treatment.
Very good.